It's a great pleasure to again get a chance to talk to you all this morning. Let me get started. Just want to make sure I get my timer here going. All right. So today's topic is searching for anomalies in anomaly detection, and this is an area of my own research interest. And so here is the outline. As Maria Jesus just said, we'll give an introduction, then review the popular algorithms, the sort of state of the art in anomaly detection, show the benchmarking study that we did, and then wrap up with the 3 use cases, which will be data cleaning. So given a data set, try to find and remove contamination outliers. The second is fraud detection, and the third is runtime monitoring of a classifier, as I discussed yesterday. Okay, so what do we mean by anomaly detection? The goal really is to deal with contaminated data. So suppose that our data looks like this very idealized situation here on the right. The little circles are what we call the nominal data or the normal data. We like to avoid the word normal because we don't want to confuse this with the normal distribution, the Gaussian distribution. So we call it the nominal data. But then there are these other points which are denoted here by stars, and these are the anomalies that were generated by some different process, a process that's distinct from whatever is generating the nominals. The examples of such distinct processes might be measurement errors or broken sensors. It could be fraudulent or criminal behavior. It could be some novelty that was not observed during training, like a new category of objects in a computer vision system. So there are generally 3 settings in which we want to apply anomaly detection. The first one is the data cleaning case. We start with a data set. There's no test data. We just have a single data set, and it's contaminated, and we want to clean it. And so our goal is to identify and remove those anomalies before we train a classifier. The second case is where we have clean training data, but we expect when we deploy the system, we will face anomalies, contaminations, frauds. And so in this case, this is really, in some sense, the nicest case because we do have clean training data, and the anomaly detection algorithms work better when the data is clean. But now the goal is at test time, that is after deployment, to detect and reject the anomalies, or at least flag them for analysis. And then the third case is the most general, where we have both. We have contaminated training and contaminated deployment data, and we need to deal with them both. Well, why not use supervised learning? If we have training data where we could go through and try to find the anomalies and then label them, and then train a classifier to distinguish the training data from these anomalies. But there are 2 reasons why we don't want to do that. The first is that, fortunately, anomalies tend to be rare. And so that means we might have only 1% or 1/100th of a percent, or even 1/1000th of a percent of our data might be anomalies. So we won't have enough training data to train on. We call that, extreme class imbalance. But the other reason is that we don't want to assume that the anomalies that we'll see at deployment time are the same as the kind that we were seeing at training time, right? Especially think about fraud detection. The people who are trying to break your system, attack your system, they're not going to just stay stationary. They'll change their tactics, especially as they discover that you have a good machine learning approach to finding them. So we don't want to make that assumption of stationarity. So there are generally 4 anomaly detection strategies that have been studied in the literature, and let's go through those. So the first is density estimation. And this is the first thing I think that anyone with a mathematical mindset, the first thing that comes to their mind is we're given a set of training examples, and we'll want to fit a probability density function, some sort of probability density model that assigns high probability density to where the training data are and low density everywhere else. And then back in 1948, I believe it is, Claude Shannon introduced information theory, and one of the concepts of information theory is called surprise. And surprise is the negative of the log of the probability of an event. And the intuition there is that if an event has probability 1, then we should have no surprise about it at all. And of course, the log of 1 is 0, and so we have 0 surprise. On the other hand, if an event is impossible according to our model, it has probability 0, then the log of 0 is negative infinity, and so when we negate it, we are infinitely surprised by an impossible event. And it behaves well in between those two extremes also. So should we try to do density estimation? Well, we can, and a very popular density estimation technique that works very well is called kernel density estimation. And the idea in this picture here, which I borrowed from Wikipedia, you see these little black markers here. Let's imagine those are 6 data points. And what we do is we put a small kernel, which in this case is a little Gaussian distribution, centered on each of those data points. And each of these little kernels is given a weight of 1/6. So it's a Gaussian distribution that you know, the area under it is going to be 1/6. So when we add up the area under all of these, you know, we'll double count these area, but we get this blue curve if we just sum those little red curves. And by construction, the blue curve will also have an area under it of 1. So it is a normalized probability density. Now, of course, if we have contaminated data, as in use case 1 and 3, we're going to put a little red bumps on all of the contaminated points as well, and that's going to be a problem. But there is a beautiful piece of work called robust kernel density estimation by Kim and Scott that uses what's called a Huber-style loss, a robust loss function, to figure out that it basically can ignore or downweight the outliers. And so it gives us a nice method. So density estimation is very elegant, and there are many other methods that you can fit ensembles of Gaussian mixture models. You can use neural networks to do deep density estimation. But the disadvantages are that in general, density estimation requires a huge amount of data. For kernel density estimation, the sample size grows exponentially in the dimension of the data. So if we had 100-dimensional feature vectors, we would need, you know, e to the 104 divided by 2. So e to the 52 power amount of data. So that's clearly infeasible. It also has a drawback that if you have a collection of anomaly points that form a tight cluster, then the density estimator will put a lot of density there, and we will not discover that tight cluster. The second technique that's used is quantile methods, and part of the goal here is there's a principle in machine learning that is usually credited to Vladimir Vapnik, which is don't solve a harder problem on the way to solving the problem you really are trying to solve. Density estimation is a very hard problem. Maybe all we want to do is figure out, say we think that in our training data there's a fraction alpha, let's say 1%, of data points that we think are the anomalies. We might make a guess in our application about how much contamination there is. That might be based on historical fraud data. It might be based on looking at a small sample of the data and individually looking at the cases. But in any case, we might have we might know that we're looking for about alpha fraction of the data being anomalous. Then the question is, can we find a decision boundary that surrounds our training data that contains 1 minus alpha of the data points? And then everything outside of it we can declare to be the anomalies. And so here we're not estimating the probability density anywhere, we're just drawing this boundary. So it's much more like classification. And this is the idea of something called the one-class support vector machine. If we use a linear boundary, of course it's a linear boundary in a kernel space, so it's difficult to get our heads around. Or if we use a hypersphere in kernel space, it's called support vector data description. And the one-class SVM is probably the best known machine learning strategy, but we'll show that its performance is definitely mixed. The anomaly score, I'll use this notation, the anomaly score of a query point xq will be its distance outside of this boundary. Okay, so the advantages of these is that the amount of training data we need is much less. It only grows as 1 over epsilon squared, where epsilon is how accurate we want to accurately hit that 1 minus alpha quantile. but it is a little bit tricky to use. It requires tuning a kernel function. Now that's true also for kernel density estimation. And the algorithms for fitting large support vector machine type models, until recently, they do not scale to large data sets. There are some techniques now that are based on subsampling and finding representative data points. But we'll see in our experiments, it doesn't perform very well if we really need to rank the points by how anomalous they are. But there was a recent paper 2 years ago by Menon and Williamson that shows a way to improve that. Okay, well, the third approach is conceptually the simplest. Let's just look at distance. So suppose we can define a good distance function over our data. That can be very challenging, but actually every technique we've looked at so far will involve some kind of a distance, because a kernel technique also requires a distance inside the kernel. So let's suppose we can choose a distance function. We can just use as our anomaly score how far away is a query point from the kth nearest neighbor, the first nearest neighbor. If something is an outlier, it's going to be far away from the data. Let's just look at that. And so this follows the intuition that points out in empty regions of the input space are very likely to be anomalies. And there's an improvement on this simple idea called the local outlier factor, or LOF, and that normalizes the distance to our nearest neighbors by their distances to their nearest neighbors. So sort of a recursive idea. So if you're in an area where things are denser, you need to be, you don't have to be as far away to be considered an outlier. And the advantages of this are, of course, it's very easy to understand conceptually. It's also fairly easy to tune, and it performs quite well. But it has the same failure as the as all of the previous methods, actually, that if the anomalies form tight clusters, then it's very hard to tell them apart. In fact, that's a property that's true of all of the methods that I'm describing. A bigger issue is that a naive implementation requires computing all pairwise distances, which is a time that's quadratic in the number of data points. And the biggest problem is you have to store those training instances because you need to look them up at classification time. Some of the other methods I described, the support vector machine, for instance, you only have to store a subset of the instances. And so you have a much smaller memory footprint. Okay, well, the fourth family of methods I call the projection methods, for lack of a better word. But these are ones that somehow break the data up into lower dimensional spaces. And the particular one I'm going to describe is called the isolation forest, which was developed by Lo, Ting, and Zhou about 9 years ago. Liu and Ting were at Monash University, and Jihua Zhou is a famous researcher at Nanjing University. So the way it works is it basically builds decision tree style of objects, fully random binary trees. So at each node in the tree, we choose one of the attributes, one of the dimensions at random. Look at the range of observed values of that dimension, so the minimum and maximum value along that dimension, and randomly choose a splitting threshold, theta 1. So we might choose temperature, and we might randomly choose 32 degrees. And then split on that, and then do the same thing recursively, and recursively, until every data point is in its own leaf. Now, from a machine learning point of view, the alarm bells should be going off. What? You're overfitting the data terribly if you're going to have all your leaves contain only one data point. And that would be true, but the reason we're doing this is to calculate what's called the isolation depth, which is how many tests do we have to traverse to get to the leaf. So we would say that this point here has an isolation depth of 3. And the intuition is, in some sense, we're throwing random splits at the data. And if a data point is an outlier, it should take very few random splits to separate it from all the other data. Whereas if a data point is buried inside a very dense region, then it might take many hundreds of splits before we isolate that data point from all the others. Of course, if there are data points that are absolutely identical, we consider them isolated if they both reach a leaf. So we build a forest of these trees, an ensemble, say 100 trees, for example, and we let d bar of xi be the average isolation depth of data point xi. And then there's a way to normalize this to get based on the expected depth from a theoretical calculation. And so our anomaly score is on a scale from 0 to 1, where anomaly score is larger than about 0.5, signal that it's anomalous. Okay, well, so there's a huge literature really, especially in the data mining world, of anomaly detection algorithms. You know how the machine learning community can go wild exploring different ideas. And so back in 2013, my student Andrew Emmett and another of our students, Shubhamoy Das, working with Alan Fern and Wen-Kim Wang and me, we decided to do a benchmarking study to try to compare all of these methods in a careful and objective way. So we looked at 8 different algorithms. You've seen most of them. I didn't talk about ABOD or LODA, but we don't have time for that today. But you can read about it in these papers. Okay, so the methodology was to take 19 data sets from the UC Irvine dataset repository, choose one or more of those classes, because these were mostly classification data sets, and declare some of those classes to be the anomalies and the rest to be the nominals. And then we systematically manipulated the relative frequency of the anomalies, how difficult the individual anomaly points were, that is, were they buried inside the nominals or are they easy outliers? We added irrelevant features in a controlled way, and we tried to choose points that either formed clusters or were very dispersed. And we made 20 replicates of each configuration. Some of the data sets, we filtered out ones that were absolutely impossible. And the result was 25,685 individual benchmark data sets. And then to evaluate these machine learning methods, we measured the area under the ROC curve for just the binary decision. Is a query point nominal or is it an anomaly? We were really in, I would say, scenario 3, contaminated training data, contaminated test data. As you're familiar with the area under the ROC curve already, here we can think of it as the probability that the anomaly detection system is correctly ranking a randomly chosen anomaly above a randomly chosen nominal point. And we actually transformed the AUC into the log odds because we did some linear modeling with this. And we also looked at the lift, which is the average precision divided by its expected value if you were guessing at random. And then we also log transformed that, so the log of the lift. And so here's a plot I showed you this yesterday. On the vertical axis is the change in the metric, either the change in the AUC or the change in the lift, compared to a control data set, which we used as a baseline. And what we found was that the isolation forest was generally better on both the area under the ROC curve and the lift. And then there's sort of a 4 or 5 way tie for second place, right? So the local outlier factor and the robust kernel density estimation, they're doing very well also. This was an ensemble of Gaussian mixture models, which was quite good. And then the big surprise was this is the one class SVM and the support vector data description, and they performed very poorly. And I think part of the reason was that we had to have a completely uniform way of tuning the parameters, the kernel parameters and the alpha parameter. And so so I think that shows that these methods are very sensitive to the setting of those parameters. Okay, well, the challenges then that we see is that, in summary, is that high dimensional spaces are inherently difficult. Right now, the frontiers, this is really what are the frontiers in anomaly detection today. In our benchmarking, we did not work with any image data, but images are clearly the frontier, and also time series. And these are very high dimensional spaces. And we know from the theory of kernel density estimation that these are very challenging. So one question that comes up is, well, can we safely assume that the data live in some lower dimensional subspace? Maybe we could discover that subspace and then do our modeling there. And that's clearly true for image and video data. And so promising directions are there are a lot of people looking at autoencoder type methods and generative models like GAN. And there's some interesting models like the neural rendering model. And there's a lot of work in time series as well. But these are still academic explorations. I don't think anything is really ready for widespread application. Okay, well, let's now talk about these 3 use cases that we'll be examining with BigML in Guillem's session. Okay, so the first one is data cleaning. So we've been given a data set. We suspect that there are some problems in it. Maybe there were data entry errors. Maybe there's fraudulent transactions. Maybe it's based on sensor data, and some of the sensors were broken. I have a big project in weather and network data, and our weather sensors get dirty and they fail and so on. So what we want to do is fit an anomaly detector to the training data, and then examine the points that have high anomaly scores and remove the ones that are suspicious. And of course, visualization is really a critical tool here to somehow be able to visualize your anomalies or get explanations for why each of the points with high anomaly score, why does the learning algorithm think it's anomalous? The second use case we want to look at is fraud detection. So here, the pipeline is something like this. You want to clean your training data as best you can. So if there are known frauds, you want to remove them. Then you want to train the anomaly detector. And then the idea is to set things up like this. You get your new data in, you apply anomaly detection, and then you score them all and you rank the candidates. And you take the top ranked candidate and present it to your fraud analyst, and they look at it and say, well, does this look like a fraud case? And if yes, they launch an investigation. If no, you show them the next ranked candidate. But what we found is that we can do much better by incorporating feedback from that fraud analyst. So we now use this strategy instead. The data comes in, we score it, we compute the top ranked candidate, we show it to the analyst, and the analyst says either yes, launch an investigation, or no, this is a false alarm. But in either case, we feed back the answer to the anomaly detection, and we use this to re-rank the candidates. And so we've had 2 different methods that we've developed in our group, something called AAD, which was active anomaly detection, and more recently GLAD-OMD, which was published at KDD a year and a half ago. And here are some of our results. So on the left is a plot for a benchmark data set. This is the ANN thyroid data set from Irvine. And what we're showing on the horizontal axis is the number of times we've gone through that loop. So right here, we presented the top ranked candidate to the analyst, then with the second ranked, third ranked, fourth ranked, and so on, all the way up to presenting 100 candidates to the analyst. The vertical axis is how many of those were in fact true anomalies. Now, of course, this is all on the left panel. This is simulated because we had the right answer in terms of having trained with supervised learning, trained a classifier to classify things for this data set. And so that classifier could be a stand-in for our analyst. And what we found was that if we just present, the bottom line is if we're just presenting the candidates in score order, then we can find about, I don't know, 22 of them maybe. But if we feed back the analyst's feedback to the anomaly detector, with GLAD-OMD, we could find about 52, and with this, AAD, 52, and with our newest technique, GLAD-OMD, all the way up to about 70. So you can see this is, we went from a false alarm rate of roughly 20 to a roughly 80% false alarms to only 30% false alarms. So a massive improvement in our ability to find these anomalies quickly. So these results are super wonderful, and I was very suspicious of them because, of course, this is not real anomaly data. This is taking a classification problem where the anomalies are really in different classes, and we would expect them to be easily separated. But the picture on the right is for a cybersecurity exercise that we were involved in which was called APT Engagement 3, where there were 3 host computers, and there was a red team that was attacking those host computers with advanced persistent threats. And we were monitoring network traffic and system calls and things like this, extracting features and then running them through our anomaly detector. And what we're plotting now, vertical axis, is the number of times through the loop, so sort of like the horizontal axis here, number of times through the loop before we detect the first true intrusion. Okay, and the orange bars are the baseline. So on host 1, it took about 42 false alarms before we found our first true hit with a high variance. Whereas if we use our feedback from the expert, it only took 3 false alarms before we had the hit. So again, more than a factor 10 improvement in our effectiveness. Of host 2, the story is similar. With the baseline, it took 60 something, and with the feedback, 10. And the third host, we only have a factor of 2 improvement. So I'm extremely excited about this kind of result. And I'll tell you, well, I don't have time to tell you how the algorithm works, unfortunately, but you can ask in the breakout. Okay, so the last use case is runtime monitoring rejection. So the basic intuition here is that classifiers work well in regions of the input space where there was lots of training data, but the outliers are in sparse regions. And so maybe what we should do is when we're given a query that falls into, that gets a high anomaly score because it's an outlier, maybe we should not trust the classifier, but instead reject this point and say, I'm sorry, I refuse to classify this because I don't think I'm going to get it right. So this is rejection based on anomaly scores. But as I mentioned yesterday, we might also want to just flag the data point and say, this is an anomalous one, and then and log that, and then examine our logs day on day, week on week, to see if the anomalies are increasing over time. So when but then the idea is if the anomaly score is not greater than some threshold, then we go ahead and classify it. But as I say here, logging these anomalies and watching for trends is probably the recommended practice because anomaly detectors tend to generate many false alarms. Okay, so in summary, anomalies are data points that are generated by some process that's different from the nominal process. I reviewed for these 4 different families of anomaly detection strategies, and we found that generally these projection methods like the isolation forest perform best, which is why BigML offers the isolation forest in our product. And we were disappointed to find that the quantile methods, which are probably the most popular in machine learning, did not perform as well. And there are at least 3 important use cases: data cleaning, fraud detection, and real-time monitoring of a classifier. And thank you very much.